Today we start Module 5, Divide and Conquer Approach Part 2. Part A, Mergesort. 8.1, Introduction to Mergesort. All right, we work on the sorting problem, but this time we look at another different method. So this method has its advantage. So first, let's look at the problem. First, before we look at the sorting problem, let's look at this special problem. Our problem number 14, merge two sorted arrays. So what's that? All right, the problem is very simple. Given two ordered arrays, notice these two arrays already ordered. All right, that special condition. Then we need to do this. How to merge them to get an ordered array. Pretty simple, right? Pretty simple. The question is why we need to solve this problem, right? So let's look at the motivation first. Why we need to consider this problem? There must be some important reason behind it, right? Let me describe a special situation. We may need to consider this kind of problem. First, think about how to sort a huge array. How big it is. You can imagine the array is so huge and you cannot load the whole array into the computer main memory. You have to split the array in the hard drive. Originally, the data stored in the hard drive. But we know the main memory is much smaller than the hard drive, hard disk. So you have to split into smaller subarrays. Every time you can only load one of the subarrays into the main memory. Think about that special situation. How do you sort the whole big, complete, huge array? Think about that. But when we solve that special problem, very special, but it's possible. Let us use this 4-line segment represent one big, huge array. Our method still divide and conquer. So we divide it into multiple pieces, smaller subarrays. Then every time we just load one of the subarray into the main memory and get it sorted. All right. So eventually we get each individual subarray sorted. But at the end, we need to merge, right? Now you can see there is a need to do the merge operation as we describe it in our problem number 14. But when you sort those individual subarrays, definitely you can use parallel computing, right? So you can use multiprocessors. Each processor just sorts one of the subarrays. All right, but you will see there is a special situation. We need to solve this merge problem. Now the question, how to merge two sorted arrays with the minimum number of comparisons, right? We always want to get a minimum number of comparisons. All right, so here, the current situation, given two arrays that are already sorted. How to get a new sorted array that contains all the elements. Here, when we solve this problem, we need to take advantage of the structured data. The structure already imported the structure, order structure already there. We should take advantage of it. using that structure, it can help us reduce significant number of comparisons. Yeah. All right. So here, now we need to look at our old experience. Can we use some related method in this new problem? Yeah. So let's take a look. Yeah. But when we look at our old sorting algorithms, we want to avoid those methods that do not take advantage of the older information, right? Some sorting algorithms never take advantage of the older information. So what's the meaning of that? That means even if you give an already sorted array, it does not give you better performance. Even the data given already sorted, but you get a pretty bad performance efficiency. That algorithm, that sort, does not take advantage of the older information. We have some algorithms with that property. So let's take a look. The first one, selection sort. Does it use the older information? No, because even the array already sorted, you get a worst case efficiency, right? You get a worst case efficiency, that is the big theta of n squared, right? Because for selection sort, we always get big theta of n squared. Yeah. Bubble sort does not use it, its original version does not use it, but we can modify, we can improve it to make it use the older information. Yeah. Yeah, but you need to do something extra, right? So when you do that thing extra, you need to consider if you can extend it to the general case, right? Yeah. But there is a better one, insertion sort. This one really takes advantage of the order information. Yeah. Because if an array is sorted, then you will have the best efficiency, big theta of n. Even better, almost sorted. Recall, if an array is almost ordered, then this method is the best. So you can see, you compare with that bubble sort. The bubble sort, although after the modification, you can improve its efficiency, but if it is almost sorted, then you get a worst case efficiency. Almost sorted, so that's good comparison. For the bubble sort, if the array is not ordered but almost ordered, yeah, but your modification method may not work well, right? So think about that. May not work well. So that tells us this insertion sort at this point is the best candidate that can help us work on our current question. Yeah. All right. So next, let us work on the merge problem. How to merge two sorted array. Yeah. Here, we have our old experience. The old experience is the insertion operation. We want to take a look at it. Yeah. But when we use it, we like to take a different view on this insertion step. We have to modify a little bit. Otherwise, if you still use the old view, you cannot get anything new here, right? You get insertion sort, right? But we don't want to repeat that insertion sort. We want to get something new. new solution, new method. Yeah. All right. So why take a different view? Answer is straightforward. Get a new idea. We want to have a new idea and a possible improvement. When we try some new idea, we may have a chance to have improvement. Yeah. Here, so let's look at what kind of new idea we like to have. First, this is insertion situation, the typical insertion situation. We insert a new key V into an ordered array, right? Yeah, but here, let us look at this in a different way, different view. This time, that key, that V, can we treat it as a one-element array? Yeah, one array that just contains one element. And that one element array must be sorted, right? Yeah. So here you can see we have a very special case. Actually, we have a case that we try to merge two ordered arrays. How about that? So this is a new view. Yeah. Although it's a very extremo case, right? Just one array has only one element. The extremo case. Yeah, but it's fine. We can change that part. Yeah. The new interpretation is two sorted arrays are combined to get a new sorted array. Yeah. So this new view, that is the merge view. Merge two sorted arrays for a new sorted array. So here you can see the connection. Yeah. Insertion operation and the merge view, you can see closely related. Yeah. All right. So next, we want to apply this merge view for our new problem. Yeah. Apply merge view on two subarrays. But this time, when we look at the insertion special case, the data size k and 1. The first subarray size k, second size 1. Here we notice the data given not quite balanced, not balanced. Okay? And we have experience, we know if the data distribution, when we split data into two subarrays, if the split is not balanced, it may cause poor worst case problem. The worst case, we want to avoid that kind of unbalanced data split. Yeah. So the improvement is, in order to avoid worst case, if it's possible, we want to apply the balancing principle. Balancing principle. When we have some freedom of choice, when we need to make a decision, we try to split our data as even as possible. That's the balancing principle. Yeah. So our decision, our improved view, try to make two subarrays of equal size. When we do divide and conquer, try to make two subarrays as, the size of them as even as possible. Yeah. All right, so that's the introduction part. Yeah. Next, we will implement this idea. And we want to see what result can we get. Yeah. All right, yeah. So that's the 8.1